Hi everyone, I'm Russell. Our project focuses on reproducing, modernizing, and improving SRL-RNN for dynamic treatment recommendation. This is based on the 2018 KDD paper by Wang and colleagues. I'll cover the first half of the presentation, including the problem, our setup, the data, and the main results. The problem. The core problem is recommending the right medications to ICU patients over time. This is difficult because treatment is sequential. Doctors adjust medications day by day as the patient changes. Supervised learning can copy doctor behavior, but it does not directly optimize outcomes. Reinforcement learning can optimize outcomes, but it may drift away from safe clinical practice. SRL-RNN is interesting because it combines both ideas. The original paper reported a Jacquard score of 0.409, which became our main benchmark. What we did, we compared three models on the same dataset with the same evaluation script. First, we rebuilt the original SRL-RNN baseline so it could run locally. Second, I developed an improved SRL-RNN with a better multi-label loss and threshold tuning. Third, Jamal built a TD3 plus transformer version to improve long-run stability. So the goal was to fairly compare a reproduced baseline against two extensions. The data we use Mimic 3, a real ICU dataset with about 33,800 patients total. One of the biggest challenges was that the original preprocessing code was never released, so we had to reconstruct the full pipeline ourselves. We kept only adult patients, grouped the data in the daily windows, built features from vitals, patient details, and diagnosis, and encoded medications into 180 labels. Then we saved everything in the format the original code expected. Results at a glance. At a high level, my improved SRL-RNN performed best on the main overlap metrics with a Jacquard of 0.2553. Jamal's model had the strongest mean Q, which showed better long-run stability. The updated baseline was the weakest and had a very negative Q value, which suggested unstable learning. So overall, the baseline was runnable but weak. My model gave the best recommendation quality, and Jamal's model was the most stable over long training. Okay, so here's a deeper dive into my model. The biggest improvements in my model came from better threshold tuning and a stronger loss function. Instead of using the default threshold, I calibrated it on the validation set and found a better operating point. That helped produce the strongest local results, including the best Jacquard, F1, and ROC AUC. We still did not reach the paper's 0.409 benchmark, but the main reasons were likely missing pre-processing details, shorter training time, and limited compute. At this point, I'll hand it over to Jamal.
On the TD transformer. So let's talk about what changed and what we learned. So we replaced with LSTM with a transformer. So the original model uses LSTM to read the patient history. We swapped it for a transformer, which is better at picking out which past days matter the most for the current decision. We also use a two critics instead of one. The TD3 uses a twin critics to make the learning more stable. The baseline single critic ended up with a Q value of negative 6.98, which ours reached a better result of 3.76, which is a much healthier signal for the model. Also, the no collapse after the 10,000 rounds. So the original model actually crashed 2,340 episodes, but TD design ran the whole full 10,000 episodes without collapse, which provided like stability and shows the improvement works. We overpredicted also for what we learned is that we also make some over predictions of the medication that provided per patients, but actually the doctor actually provided only 27.8 instead of 63.5 that the model actually predicted. The model was too cautious about missing the medication, so it recommended too many. J-card score was lower than the Russell's, so actually this model performed better, worse than the Russell's model, but actually performed more stability, but the J-card was only 16%. We can also explain what model uses, like which features that influence the recommendation the most, and the top ones were the temperature, oxygen levels, and GCS score. This makes the model easier for clinicians to trust. Why didn't we match the Bever's numbers? Because we didn't have the prep code. The data prep code was never released, so there's no way to know what the original authors used. We also had a different patient cohort compared to the original Bever, so we have like a 33,849 while they had the 22,865. We also think that we didn't train our model long enough to maybe reach that number. So since we don't know how many rounds they trained, we just came up our own, in, and this gave us these results. We also used a laptop, so because since we don't use any powerful machine and we don't have any dedicated GPU for the model to train, that's also another factor that can influence our numbers. We also use only training and validation. We don't use any test set data. So instead of using uh, train, validate, and test, we only use train and validate. The original code was also very outdated. The original code was outdated, so we also have to modernize it, and remove some of the code. So that kind of influence our result. Is the paper reproducible? Yeah, I mean, in theory, for what we have as a concept, we can reproduce, but I'm not exactly as a code because we don't have the full code. But there are some things that we thought was very, straightforward. Like, for example, the idea behind the paper is clear and well motivated. Also, the design was very intuitive. The mimic 3 setting, reward structure, 180 medication tasks are all described well. The GitHub was still useful even though we didn't have the full picture. But the things, but there are things that are very difficult. For example, we don't have the data prep, like I said before. We had to reverse engineer the whole pipeline. Our libraries were old. Some of the hard-coded paths broke immediately or on machine because we don't know which machine that the original authors used. The model stability was very sensitive, so that's why actually I came up with this model to stabilize that. We also don't have any documentation for the seeds, convergence, and expected training time. So I think if the author, releases the full data prep, provide like a working environment file, and share the checking point they use to report their numbers, I think that may be possible for now, but we don't think the paper is fully reproducible. And the key takeaways, I think the model that they use works with imitation, or combining the imitation and reward-based learning is a solid approach for recommended medication for ICU patients. Also, that the Russell's actually model performed and get a better J-card score. And the key improvements that he used was threshold tuning and beta loss function, which may be interesting to explore more. I also use a TD transformer, which made the model more stable, and the training more stable, and not crash at a certain point. So that's another thing that we learned. We didn't also reach the paper J card number, mainly because we missing the processing code, and we also have a limited computation capabilities, and also the training time constraints that we have. For anyone reproducing this work, the budget extra time for data prep may be useful. Using a larger training episodes, and also calibrating your prediction threshold may be also useful from what we have learned. Thank you so much.